So that's the goals for today. And so this is really a continuation of context-free grammars. So we know that context-free grammars are a very powerful way to express non-regular languages. And so far we have seen how to generate these types of languages. But today we're going to look at it from the other side and introduce this computational model that shows how we can recognize these non-regular languages. And so a nice analogy to understand just the context of PDAs, we can say that, it's a little thinner. Okay, so we can say that regular expressions are to NFA as CFGs are to PDA. And so this is really what we're going to do in the coming classes, as we discuss PDAs, is we're going to do very similar things that we did earlier in the class, where we're showing the relationship between regular expressions, which generate regular languages, and NFAs, which recognize these regular languages. We're going to do the same thing for CFGs and PDAs. So they're really a parallel concept. And so we know that regular languages are defined as languages that can be recognized by finite automata. And CFGs are expressing context-free languages, which finite automata are limited. They cannot recognize those languages. And so we need an extension of those finite automata in order to be able to recognize our context-free languages. And this brings us to a PDA. And essentially, a PDA is it's very similar to an NFA, but we have what we need to recognize these context-free languages. We always said we need memory. And so a PDA is going to be an NFA with some additional memory. And what does that look like? The kind of memory that a PDA has is a stack. So a PDA, it's essentially an NFA plus a stack. And so let's remember first what a stack is, because it may have been a while since you used these, right? So remember that a stack is a data structure. Times draw it like this. And a key aspect, a key attribute of the stack is the way that we access the data, right? And so I often call it a LIFO stack. Does anyone remember what that stands for? Excellent. Daniel and Leah and Rachel, Emily. Okay, great. I'm really glad you all remember that. Good. Last in, first out. Great. So this is telling us how we access data. We put in data at the top of the stack, and we also take out data from the top of the stack. And there's different kinds of examples of stacks in real life. So for example, a stack of trays in the cafeteria, where you always put your stack at the top and you always put your tray at the top and take a tray from the top, or a can of Pringles, where you can put in at the top, but you can only take out a Pringle from the top. You can't reach a Pringle from the bottom. And so these are, so this is a stack. We can only access the top of it. And so an NFA is limited, right? Because it doesn't have this type of memory. So we can draw an NFA. Here we have our kind of an abstraction of an NFA, and the NFA can process input. Maybe we have something like this, and our NFA can read the input string and process it one symbol at a time. and it can make decisions about what state to transition to based on the current state, but it's unable to recognize our more complex context-free languages because it can't really store information such as, keeping track of counts of things or being able to balance strings like we've seen with our CFGs. And so our PDA needs to be able to do that. And so it's going to be, we'll have our PDA here, which is also going to be processing some string, some input. But in addition to reading this string, it's also going to be keeping track of this stack. And so this gives our PDA a lot more power than an NFA. And this gives us the ability to have a significant amount of memory. In fact, the stack can have infinite memory. And so this will be the key that will allow our PDA to recognize our context-free languages. So this is kind of an introduction to the concept. Let's look at an example to see how this works, how a PDA can use a stack to recognize a language. Okay, great question, Zachary, about the kind of data stored in the stack. Let's take a look and we'll see. So here's a language. We like this language. 0 to the n, 1 to the n. We'll add to this. Let's just say, oops. Let's say n greater than or equal to 0. And so take a look at this language and let's first answer a quick poll about this. Is this language a regular language? So remember the definition of a regular language. That means that we can construct an NFA to recognize this language. Is that true or false for this language? Okay, it'll take 5 more seconds. Okay, great. So this language is, in fact, not a regular language, and we cannot construct an NFA to recognize this language. And the reason is because it doesn't have the memory to be able to, we have to keep track of the number of zeros and then check to see if the number of ones is equivalent. And an NFA doesn't have that capacity. But now that we have a PDA with a stack, we're going to see how we can use a stack to recognize this language. So how does this work? So first, let's describe it kind of informally, just the idea of it, the intuition, and then we'll formalize it with our formal definition. So imagine you have a string of zeros and ones, and you have a stack. How can you use the stack to check if the string is in this language? So think about it. Think about how you can, and remember, we're going to be processing this string one symbol at a time. And somehow we want to use the stack to check if it's in this language or not. So let's think about how we can do this. So we're going to read, oh good, I'm glad to see some ideas here. Good. Excellent, Pavel, you're definitely on the right track here. And Atar, super. Good, so the idea is that every time you see a 0, we're gonna push it on the stack. and then we're going to pop it every time we see a 1. Actually, we should just quickly review our stack operations, right? Our operations for our stack are push and pop. And we're always working with the top of the stack. So when we push, we can push it from the top. And then when we pop, we're adding elements to the stack when we push onto the stack, right? Like adding a tray to the stack of trays. And then when we pop, we're removing the top element from the stack. Okay. Mahmoud, that's a good question. So in this theoretical, we'll see soon the definition of our PDA. We're not going to have get size. And we're also not going to have is empty. So we'll have to handle that. And thank you, Mark, Mark is here answering questions on the chat too, and also on the Q&A panel. So remember, you can ask questions there. Okay, great. So we have our language, and now let's describe how a PDA can recognize this language. So we're going to read each input symbol, and we're going to do this one at a time. So I'll just write this out. Read each input symbol. One at a time. And good, as a lot of you said, if we see a 0, we'll push it onto the stack. And then remember what this language is, right? It's an equal number of zeros followed by an equal number of ones. So after we've read all the zeros and pushed them onto a stack, for every 1 that we see, we're going to pop a 0 from the stack. And essentially we're matching each 0 with a 1 and checking that they're an equal number. So after we read all the zeros, if 1, pop a 0 from the stack. Okay, good. And then how do we know if we should accept our string or not? So if at the end of this process, we've reached the end of the string and we have an empty stack, that means that we had a perfect match for every 0 and 1, and we can accept. So we'll say accept if the stack is empty at the end of the string. And we'll reject there's a few possible cases that we would reject. So what are some reasons why we would reject a string? Okay, great, Kartik. So if the stack is not empty at the end, then we reject. And that means that we had too many zeros. We had more zeros than 1. So if the stack is not empty, right, then we had more zeros than 1s. Another case is, great, Emily. So if the stack is empty too early, we had more 1s than zeros. That's another case. And then another reason to reject is there's also another constraint, not just that it has an equal number of zeros and ones, but that the order is 0 to the n, 1 to the n. So if we ever have an incorrect order, if we ever read a 0 after a 1, then that's another reason to reject. So that would be incorrect order. So we can see how we can use a stack to keep track of information, to use that as memory to be able to check if a string is in this language or not. So this is kind of an intuition of how we might use a stack, but of course we do have to formalize this. And so we'll start with the formal definition of a push-down automaton, and then we'll see how we can formalize this process with our PDA. Okay, so far so good. Any questions? Okay, so let's move forward with a formal definition. And, oh, one question, Rodney. The last one, yes. So if at any point that we're processing the string, we see a 0 after a 1, that means that the string is not in the correct order, right? 0 to the n, 1 to the n means we need to have an equal number of zeros followed by an equal number of ones. Great. So the formal definition of PDA, so this is just copied from the book, and we'll go through it together. So we said a PDA is essentially an NFA plus a stack, and you really see that with the formal definition. It's very, very similar to the formal definition of an NFA, which was a 5-tuple. And now we have a 6-tuple. We're just adding one thing to our definition. And does anyone see which number here was added? Which of the elements is new here from an NFA compared to an NFA? Great, number 3 we haven't seen before. Let's go through it together and just make sure we understand it. So a push-down automaton is a 6-tuple, and we'll go through each one. So the first is a Q, a set of states. Seen that before. Sigma is the input alphabet, also same as usual. Then we have the upside down L, right? So that's gamma. And gamma is the stack alphabet, right? So we're adding a stack, and so we have a stack alphabet. Number 4 is our transition function, also different. We'll go through that and break it down. Then we have Q0 as our start state, and F is our set of accept states, and this is a subset of Q. Okay, so let's talk about, so the stack alphabet is the symbols, that's number 3 here. So it's the set of symbols that can be written on the stack. And we'll see that in an example soon. But first, let's break down the transition function, just to make sure that, because the transition function is really the heart of the PDA, that tells us how it works. So this black. Okay, so we have our transition function delta, and the function is defined by 2 parts. We have the domain and we have the range. Right, so here is our domain. That tells us what are the possible inputs to the function. And then we have the range here. Which tells us the output.